Welcome to the lecture series on object oriented analysis and design. Last two lectures we have been looking at the most important and the most difficult aspect of OOAD, namely the object identification. We do not have so many techniques that can clearly tell you that these are the objects, you please go ahead. However, it is always easy to make a statement that please do the analysis, identify the classes and objects, put together the objects and classes, you will get a bigger solution. It is more easier said than done. We have defined this paradigm which requires a completely different way of thinking, and one of those first ideas that we started using to identify objects is in a well written specification, requirement specification. Well written includes not only the technical aspects, but also the non technical aspect. These were called non technical edits, they only concentrate on the English. Plenty of difficulties are there, every endeavor we have challenges, not difficulties, but we have challenges. We have faced some stiff challenges, we have shown some good success stories. Textual analysis, if it is written well, every part of the speech will indicate something about your object oriented paradigm which you may use. Tangible entities in the application domain, this is built around the domain expert. It has a complete focus on the domain. It is paramount to telling that if you want to write a piece of software to control the air traffic control system, the simplest solution is you please go sit down in the ATC and then find out for yourself what are the objects that they use, how they do it. Or as we talk in other domain systems, those who are experts, you please draw their expertise. How to model, express, represent an innate expertise in somebody's mind is very difficult, including for the expert. Even the experts have the same trouble, they can do it, but they can't express. It is lot more easy to swim rather than write 40 pages on how to swim. These are the difficulties, that is how the human endeavor is all about. So, what we have done is a good cross section of complex problems are definitely solvable in a better manner using OOAD paradigm. There are 6 or 7 other paradigms outside of the structured programming paradigm that have shown that in these niche areas, in these specific areas, this particular paradigm will do well. Take for example, the list processing, the functional programming paradigm, which is banking on list processing, it is good in certain AI applications. The logic programming paradigm is very good in certain other artificial intelligence kind of applications. So, we are not looking at a paradigm, we do not have, even though we have been searching for, we have been trying arriving at a paradigm that will be good for all, we have not been able to do that. Object oriented paradigm has addressed complexity exceedingly well, has been readily appealing to people who get on to the task mode. We know how to flip it back into the context, flip it back onto the domain, flip it back onto your business dynamics, flip it back onto the stakeholder, because the strength of object oriented analysis, the strength of object oriented software engineering is that. So, we have seen textual analysis, tangible entities, behavioral analysis, scenario analysis. Scenario analysis is more like state machine model, but then behavior is also about the state. Scenario, something will fit, either the data or the state, we can do these two things together or separately, some idea about objects will come. The final one is the database approach. Now, database approach is what we have been talking about for so many years. However, it is just about what I want to model, it is not what should be modeled. Suppose I want to represent a microwave oven, can I model all this in database? It is very difficult. The database paradigm will simply tell me the microwave oven has these characteristics, it takes a table, it tells me this many microwave ovens are there, but the action is completely missing in the tables. However, we know that the entity relationship idea has been very strong in a field called databases, where structuring is of paramount importance. The entity relationship ER model, ER diagrams have enabled the field to develop at a very rapid pace. Data is not new, data processing is not new, but the way we represented it in the machine made it a fantastic idea, simple, elegant, backed up by a good theory. It tells me the proof correctly. Out of 20 million records, if I am getting only one record, still the proof can be given to them. It is not that we are talking about complete proofs, but then there is a verifier, there is a validator. The database model, database idea has given us what is called an entity as much as I want, whereas an object should be how much it ought to be in the bigger picture. That is difficult to catch. None of these 5 methods is complete, none of these 5 methods is foolproof, none of these 5 methods is comprehensive. Each has its own set of challenges, but then we are able to make a very good start, and we strongly believe that if we move to unified modeling language, then you are going to do better, because it gives you the best perspective from all these approaches. So, microwave oven operation is difficult. This much will I fit it in a database? It can't. Stimulus, description. So, these are all some good complex exercises. State is there, description is there, data is there, actions are there. However, nothing is comprehensive. It is a good idea. This much of a flow chart action is not in database. It is not in scenario. It is still found only in the software. It is a program, it is a flow chart. That is how we started looking at it. So, should I draw the full flow chart to get the objects? Then we will miss the objects, because flow chart is taking you into action, action after action, action after action. So, the structured programming paradigm was good until we have cited some components, but then we are not able to cite components in the traditional techniques. So, therefore, what did we do? We started moving further, more complex. This is a simple idea again. Microwave oven is something which we can easily imagine. We know what exactly is happening with the oven, but then we think that is very complex when we want to talk about analysis happening in the way which I have described. So, entity relationship model we can normalize. Now, the concern here is that the real world object is missing. What is a microwave oven? It is a set of 8 attributes. You are calling it oven, I can call it something else. The theory, in theory, it is always possible to fill that attribute called, let us say, Indian captain, and some captain, let us say Kapil Dev is already there, and it still appears for a quick eye that is acceptable. Maybe Kapil Dev is a captain even now. So, one field is there, captain, Indian cricket team captain. So, we have been talking about all these ideas. So, for example, the database approach is good, but then talking about Kapil Dev, just to give the example, one of his finest knocks in the World Cup never got recorded. There was no recording. How will you get it? They started working. It was a challenging problem. He scored something like 175 not out, and India won when nobody else was opening the score or single digit scores. His score was the match winner, clear match winner. But then there is no recording like it was before. It is one of the finest game changers. Indian cricket was never the same after 83 World Cup. So, they started doing something. It was taken up as a challenge, saying that can we find out. People would have done, by that time UK, it was in UK, they had some recording, camera recording, can we get it, some snapshots. I do not know, I am not too sure, I am not avidly following that problem, but it was a challenging problem. How do you get it now? Can you solve that problem? The answer is very difficult, very, very difficult. Is there a commentary? Is it recorded? There definitely exists. Since it is a World Cup match, there must have been, but then there is no telecast in that sense. It never really got recorded. That is what we understand. It was a big problem. So, we do not have the connectivity to the real world modeling at all. We can get some data, we can get some snippets, we can put them together, but it is very difficult. So, the ER model was doing well because it is well structured, amenable to a mathematical analysis called relational calculus or tuple calculus. Since there is a calculus, since there is a mathematical background, we know that if we do like this, we are not going wrong, we can do it correctly. ER model is like that. What will you know about the object? The object is not visible in this exercise, neither the relationships are meaning what I should think of. So, once again we said we are slipping into the old world structured model, which has not been taking us far. We have been complicating more and more, but however, please understand that these handful of techniques give us 5 different perspectives from which we can identify objects. One may be difficult, but if you put more and more perspectives, you will find the objects, you will find the classes, then you would do better object oriented programming, and the paradigm helps you. The relationships are all well defined. This is where we have been telling that in the beginning when I said associations, they are all mappings, one to one, one to many, many to one, many to many, then you can control it. In theory, it can be in any manner. This is the input, this is the output. How is it mapped? If you know the mapping, you have half solved the problem. The relationship, how the associations are being formed. So, if the associations are in conformance with our typical sets and relations, we have half solved the problem, because mathematics is very powerful, the abstraction is very powerful. You can simply go from one to the other end seamlessly. We can solve complexity like that. So, this is set, input set, output set. How are they related? If they are related in our typical sets and relation, modern algebra, school algebra, that is the algebra we are talking about, then we can solve it at a rapid pace. Very quickly we can find it out. Now, the concern here is that it is very difficult in real life to have only these mappings, or we will simply draw a line saying that in our program only these mappings are allowed, because it is easy to prove, verify. 100% verification and validation is very much a challenge even today. We are not able to do that full formal proof. So, what we did is we used all these ideas, put them in that unified modeling language, and now we think that there exists a way of coming up with some methods, general object oriented design. You do like this, like this, like this, you follow this method, you are all right. So, it is something like, in the school days we had a long arithmetic expression. The method is BODMAS, first brackets of division, multiplication, addition, subtraction. BODMAS is a method, it works. How much ever complex the expression is, you are not lost in doing it, but then once you got this method, we are not seeing the expression completely in any manner. Very quickly find out where are the brackets, solve it, off, solve it, wherever that OF off is there, division, multiplication, addition, subtraction, you have solved the mathematical problem correctly. The method is like that. We have had shortcut methods in solving problems, we have had some simple thumb rules. All this is fine, but then there should be adequate formalism, otherwise it becomes very difficult to get into the business context. We need some adequacy, some reasonable assurance, otherwise business context will be different. Maybe narrow scope method, it may be a very broad method like what we are telling now. Some are only analysis methods, some are good only for design methods, some are very preliminary, class, responsibility, collaboration. About 6 or 7 people teams can sit down and then find out. This is where it emphasizes the roles and responsibility. So, there are grades of complexity which these methods can address. We cannot use the same formula for all problems, but then these methods will tell this is the grade of granularity which we can address. Within the limitation of the method, when it is used, it delivers an assured output, an assured result. Our success rate is more or less predictable. We talked about OODLE, we will talk about all these methods later. Unified modeling language is an outcome of what we called method wars. Each one was claiming that that method is the best, it is a supreme method, nobody can beat that supreme method. Everyone was telling the same, this is a supreme method, this is a supreme method, tomorrow we will come up with another method. There were so many methods. Once again there was a torn field. The more the abstraction, the more the common base, the more strong will be the domain and the way in which we build, we progress further. We have fragmented again on methods. Every day one method was coming. Tomorrow you can create one more method and tell that under these circumstances for this purpose it is good. Code Yodan method is well known, Peter Code and Yodan Edward Yoden have been wonderful in the field of structured systems analysis and design. They have done a very nice job of not drawing us or dragging us into structured, but teaching us how that experience can flow in on object oriented analysis and design. Rumbaugh's method withstood, Booch's method withstood, Jacobson's method is there, that is the that is a nice method which he has come out with. So, Ivar Jacobson, Rumbaugh and others, Booch, all these three were becoming very dominant methods. Booch method is a surprise because it was a very high level abstraction which we thought will not be able to make it up for the pragmatics, but it did well. Booch method, Rumbaugh and others, and Ivar Jacobson's method which gave us use cases, these were very nice methods. All these three stemmed the method wars, and an outcome of using all those ideas that came when we were talking about methods is the unified modeling language. For every aspect, the UML will give you lot of perspectives. It is like seeing the same thing from multiple viewpoints and then assimilating. Eventually the cogency will come, the objects will come. I do remember very early days in my work on object oriented analysis. I was lucky to talk to a person called Martin Senger, who was working in a pharmaceutical company. He has been specially trained in object oriented exclusively to the domain of drug discovery and pharmaceutical. The way he looks at it is something which is fantastic. He is a domain expert who went on to learn object oriented. So, some kind of an interdisciplinarity is what has shown us some remarkable successes. It shows that this is how it is. No bar on using domain expertise, but then when you use domain expertise along with this, it is very useful. So, key advantages: design patterns, basic provisions for distributed architectures, eases the coding phase. So, we have virtually, as I said earlier on in one of the lectures, early lectures, now you have a UML diagram, it is approved, it has been taken care properly in terms of reasonable degree of verification and validation. Simply choose an automatic code generator, select the language, and out comes the code in the language of your choice. Eases the coding phase. Now, why model? Analysis through the construction of system models whose modeling constructs are based on formal definitions is helpful for the following reasons. Models based on formal definition can provide a foundation for testing model integrity and completeness of analysis. You can't do this repeatedly. We simply give the model, based on the model you can verify, validate, check for completeness. Since formal model definition ensures a consistent interpretation, it can provide a mechanism for communicating system understanding within this analysis team. A model with formal foundation can also improve communication with parties outside the analysis team. So, this is how the model tells. We can have some toy models, we can have some miniature models, we can talk about all these things, but model has a purpose, a specification that tells what is the reason why this model has come, and it tells what it is meant to do. So, we talked about an object model. In the context of analysis, it tells so many other things. Object oriented software engineering. We are using a technology paradigm called object oriented and trying to do software engineering. What is the most difficult aspect? Object identification, which forms the analysis. The terms are the same. Specification we hear, analysis we hear, design we hear, but this paradigm needs a completely different way of thinking. By saying so, it is not throwing away whatever is existing before, but drawing some valuable lessons and proceeding further. If we can do that kind of a focused work, there are a world of applications that are waiting, a complexity level that is intellectually stimulating and challenging. Object design is modeling. Please understand that it tells you the design, a model will tell you the design, analysis automatically. We do not need a ton of documentation, it tells so many things. So, we have been thus progressing in this method of working, and we now need to understand these two terms, analysis and design. There is no industry wide accepted definition of the terms requirement, analysis or design. The definition of these terms are often the subject of most religious debate most of the times. We have been fighting, we have been having controversies. Till today we do not know where analysis stops and design begins, or when design should take over everything else. What is a requirement? These are very difficult questions to answer. So, what we have been doing is, we have been trying to do this object oriented analysis and design in a manner which we have been discussing, so that without getting into the controversies, hair splitting debates on all these things, we can manage. Requirements and non-requirements. The requirements should form a contract between the developer and the customer. How does the customer know what he requires? Very difficult. How does the developer dictate, say these are your requirements? Very difficult. Therefore, we do not define what is the requirement most of the time. As the dialogue progresses, as we iterate, requirements will emerge. Requirements will happen in a elicited mode or gathered mode. Eventually, we understand that there are certain things that are unambiguous, interpretable in only one way. Testable, compliance or non-compliance can be clearly demonstrated. Binding, the customer is willing to pay for it and is unwilling to not to have it. It is very clear, either he wants it, not want it, he can pay, he wants to pay for it, he does not want to pay for it. Per the above definition, the following are not requirements. The system shall be fast, there is no conclusivity. The system shall be user friendly, the system shall be maintainable, the system shall be blue, assuming no one really cares what color it is. These statements are either ambiguous, untestable or non-binding. Therefore, they are not called requirements. That is the first definition we have. In other words, a requirement should have some qualities: unambiguous, testable and binding. Otherwise, please do not call it a requirement. Only after the requirements, requirement analysis begins. After we understand this, the analysis phase can begin. So, we started avoiding all these statements, generic statements. Separating requirements by kind. If we had perfect implementation technology, a computer with infinite speed, unlimited memory, transparent interface, no failures and no cost, which of the requirements would still need to be stated? This is both the strength of the requirement phase and also the primary weakness, because we somehow do not want to bind the requirements with technological perfections or imperfections. Technology will happen, if not today, tomorrow. Best of the technologies were not there when they were thought of. When they were thought of, they were all called science fiction. After 4 decades, 5 decades, technology happened, but then people were thinking that should be feasible, technology should be feasible. So, what we said was, let us not complicate our lives with the ability or inability or perfection or lack of perfection, accessibility, usability of technology first. Presuming that we have a computer with infinite speed, unlimited memory, transparent interface, no failures and no cost. What is it that you think is requirement? Then we start talking about the application. It is a very nice statement, separating requirements by kind. Every requirement that is still necessary in spite of perfect technology is an essential requirement. So, this is how we started telling that let us talk technology later. The business requirements were always taking the first position in the software engineering world. Technology was the second. Gradually, the third one, which was there, quality, became the number one. Then came business requirements. Technology slipped to the third position. Why? Because quality is the most abstract idea. It is independent of the application, independent of the technology, independent of the domain, independent of everything, independent of the stakeholder, independent of the context. quality is that abstract and it provides metrics. It does not depend on all these things, and we said quality is what reflects what we exactly want to do in software. That is the best, the close fit. We want to do quality. Please recall the first statement, develop quality software engineering. So, it is a very nice idea saying that we presume that we will have perfect technology, or it is only a matter of time when all these things will fall in place, internet speed, bandwidth. If we start talking about it, there is no end to it. We presume it will happen. The customer is not talking about it. It is somebody else who will suggest or advise, and then they will go ahead with that. Every requirement that is still necessary in spite of perfect technology is essential requirement. Implications of perfect technology, requirements about speed, cost and capacity go into the design bucket. They are done elsewhere. We are not going to spend time now. At the highest level of stakeholder interaction, we are not talking about these ideas. It is a detail coming at a later point in time. Requirements about reliability, mean time between failure, go into the design bucket. Reliability also goes into the design. Requirements about I/O mechanisms and presentations go into the design bucket. Everything shifts to the design bucket. Most of the things which we have been spending time are at a later point in time. The moment you talk about perfect technology at the first step, it will happen. It will happen like we wished. Requirements about customers' business policy, business process goes into the essential bucket. So, we have taken away 5 things. Out of 6 things, the presumption of perfect technology has given us a clear focus on what is the business process demanding, what is the customer demanding. That will be the focus, not what the technology is either limiting or flying out the customer. So, we talked about out of 6, 5 of them will go away to a later point. That is a designer's exercise, not ours. We want only what are the essential requirements. Why bother? Reduce apparent complexity. One large problem becomes 2 smaller ones. Understand the customer's business policy, business process, figure out how to automate the business policy process with the available technology. So, we split. It is a big problem, how to use technology to make my business fly. Business is like this, technology is like this, put them together. Now, we solve the problem better. Isolate areas of expertise. Business is here, the technology happens later, designer will talk about all those things, not we. All of us are not designers. Designer is a special skill. Design thinking is something which is identified as top 10 core skills everywhere. Apply the principles of coupling and cohesion at the highest level of the software architecture. More robust, less fragile systems enable separate evolution of business policy. So, the policy and the mechanism, when they are separated, the system performs best. So, in summary, we have been talking about how to manage the analysis and design, and we can have a target software architecture. The advantage of analysis and design is defined like this: bucket of essential requirements, a model of business policy, bucket of design requirements, a technology dependent model of one solution, and real live hardware software. So, by creating 2 buckets, we have grossly simplified the way we bring the stakeholders, the domains and the context and the problem and the solution and the machine together. A simple idea, it is worth spending time on analysis and design. This is the summary of the lecture. We created a bucket of essential requirements which will drive the analysis, a bucket of design requirement, this is the technology focus which will drive the design, the programming is here. A very simple view of our problem solving has emerged, and it fits well into the overall architecture. If the separation between business policy and business process is carried out throughout the architecture will guide the entire life cycle of development. Thank you. We will meet in the next lecture.